Hey everybody. So in this quick video, I want to show an example problem using the force on a charge in an electric field. So previously in previous lectures, we talked about source charges, which create the electric field. And then the test charge we put in the field, and it can actually move or accelerate or experience the force of the field. The source charges we assume are fixed in place. So as a typical example of getting a uniform or constant electric field, we often use, or one way to get it is to use a capacitor. Now, a capacitor, again, is just two basically metal plates that has positive charge on one side, negative charge on the other, equal amounts of charge, just opposite in sign. Those source charges create an electric field that points from positive to negative down in the picture here. We're going to put a test charge Q in that field in between the plates. And we're going to say the plates are a distance d apart. So a lot of times you can neglect, especially if you have like an electron or a proton, which are pretty light, actually very light, you can neglect gravity. Right? So in this case, we're going to assume the only force is due to that electric field. In that case, right, the force we can calculate is the charge times the electric field. And since there are no other forces, we can set that equal to mass times acceleration. Since it is a constant or uniform field, let's put some numbers in. But since it's a uniform field, we'll say it's 100 newtons per coulomb in this case. It is a constant force. Let's say our charge is that of an electron, which is negative 1.6 times 10 to the negative 19 coulombs. Now, an electron has a really tiny mass, 9.1 times 10 to the negative 31 kilograms. But what we can do is once we know those numbers, we can solve for the acceleration of that charge, right? In this case, the electron. So A is equal to QE over the mass. Plug in our numbers that we have up here, and we get a really big acceleration, 1.76 times 10 to the 14 meters per second squared. Now, why is that such a huge acceleration? Well, if you calculate the force, surprisingly enough, charge times the field, you'll get a really tiny force, 1.6 times 10 to the negative 17 newtons. That kind of makes sense because the charge on an electron is really tiny, but its mass is even smaller, right? It's 10 to the negative 31. And that is what makes the acceleration so big. If you have such a tiny mass, even for a small force, you're going to get a really big acceleration. If you had a proton here, the force would be exactly the same, right? QE. But the acceleration of the proton would be a lot less because the proton has more mass than the electron. In fact, it's about 1,800 times the mass of the electron. And again, that's why electrons do not move very much. Right? The electrons move around in metals, in conductors, and around the atoms, whereas the nucleus stays pretty fixed in place. So let's do one more extension of this problem. Let's say we know the distance between the plates is 0.01 meters or a centimeter. How long or how much time does it take for the electron to traverse the distance, d, if it starts from rest? So it might start, well, if it's electron, right, it's going to start down here. Remember, the direction of the electric force is in the direction a positive test charge would go. If I have an electron, a negative charge, it will go opposite the field. So the electron, I'm saying, starts down here, goes opposite the field, accelerates, covers that distance d, and then hits the positive plate. But how much time does it take to do that? Well, since we have a constant acceleration, you can go ahead and use the kinematic equations that we know from physics 221. In this case, we would use our delta x. Now it's actually moving kind of in a y direction, but by delta x, I mean the distance or displacement that it covered. VIT, now VI is 0 because it starts from rest. So what I get from my kinematic equations is that the distance d has to equal 1/2 AT squared. Now, plug in the numbers or solve for t first, right? T is equal to 2d over a and then take the square root. But if I plug in the numbers, I get reasonably a pretty small time, 1.07 times 10 to the negative 8 seconds, which is about 10.7 nanoseconds. So what this illustrates is for a constant electric field, I can calculate the force just by using F equals QE, get the direction by that a positive charge goes with the field, a negative charge goes opposite, and then I can just use kinematics like we did in Physics 221. Okay, so that's it for this problem. The next problem I'll do will have some vector nature, two-dimensional nature for the electric force. So we will stop there for right now and do the next one here.